talking about walls and filaments in the cosmic web. This talk will be the first out of two, so if you find the mathematical treatment of the cosmic web here interesting, please also attend Benjamin Hertzsch's talk, will be part 2, and he will explain how this is actually implemented in our universe. The cosmic web is a geometric structure consisting of voids, walls, clusters and filaments, which form from very small Gaussian initial conditions. So one of the miracles of cosmology is that the initial conditions of the universe were very simple, and they are simple Gaussian random fields, as you can see in the density fluctuations, temperature fluctuations in the Planck satellite, which have under gravitational collapse formed a very rich geometric shape which we know as the cosmic web. The big question I will answer in this talk is: how do we determine which elements in the initial conditions form the geometric shapes which we see in the late-time universe, in particular looking for the proto-walls and the proto-filaments in our universe. How we will do this is we will study the cosmic web through the formation of and geometry of multi-stream regions. So as you can see on the right, we have a small embodied simulation where as time evolves, the particles are moving and they form these multi-stream regions. And these multi-stream regions really capture the geometry of the cosmic web. So you see the void regions, which are single stream. You see the multi-stream regions, which form the walls and clusters of the cosmic web. And this is what we will be tracking. So one thing to note is that the boundary between the multi-stream regions are known as shell-crossing regions. And these shell-crossing regions are here highlighted in red. So you see that in the early universe, the universe was single stream. As time evolves, these multi-stream regions are forming, and you can see that by the red curves, which are first indefendable islands, which over time interconnect to form the fully connected cosmic web we see today. These cosmic web and these fault caustics, which are known as shell-crossing caustics, are really only the tip of the iceberg. So as Arnold and Sergei Shandarin and Zeldovich showed in the 70s, there exists a mathematical language which is known as Lagrangian catastrophe theory, which classifies all the ways in which these caustics can form, and they showed that these different caustics can be mapped to the different elements of our universe. However, they could only do that in 2D due to mathematical obstacles. How does this work? So what you do is you consider the mapping from the initial conditions to the late-time universe. You consider a particle, a point in the initial space, which is known as Lagrangian space, here denoted by Q, and you study how the particle moves over time to the final position x. It does it by displacing by amount s. After you consider the mapping from the initial positions to the final positions of all your particles in your embodied simulation, you can calculate the density field by considering how the particles are being stretched or squeezed or compressed. And you can see that in the density formula we see on the left. So you see that the density in a point is really determined by the mean density, which is just the overall density in the universe, divided by the determinant of the gradient of this displacement map x. As the determinant vanishes, the density spikes. This actually exactly happens when particles are being turned inside out and forming these shell-crossing regions. But as Arnold and Zeldovich already showed, the fault caustics, which are here denoted in red, with the A caustics, are only the first caustics which you can merge. There is a whole classification of caustics which we will study in this talk in more detail. So as you can see here, we have taken a small dark matter embodied simulation, and we have calculated density fields by evaluating this sum using the phase-space Delaunay tessellation field estimator technique, which is a phase-space density estimator which we implemented, and you can use it by following the link on the screen. Once you have calculated the density field, you clearly see how the multi-stream regions play a key role in the universe. You see that in the single-stream regions the density is rather low. In the multi-stream regions the density spikes, and the boundaries of these multi-stream regions are where the density spikes to infinity, which are these caustics, which we will study in more detail. So for a long time, people could only study this in 2D, but recently we have unlocked the key to understand the formation of these caustics and multistream regions in higher dimensions. So how does this work? Let's consider Lagrangian space, which is denoted by Q1 and Q2. And let's consider an arbitrary manifold in this Lagrangian space. Let's now take all the particles, points on this manifold and map them to Eulerian space using our map X. And what we see is that some points, here denoted by QS, are mapped to a singularity of the manifold on the right. It's a non-differentiable point. Now you can ask yourself the question, when does such a non-differentiable point emerge? And as it turns out, this is due to a combination of the geometry of the manifold and the mapping which sends you from Lagrangian to Eulerian space. In particular, what you can do is you can calculate the mapping X, you can calculate its gradient, and you can calculate its eigenvalues and eigenvectors. And what you find is that a combination of the eigenvalues, eigenvectors, and the tangent direction of the manifold have to vanish in order for such a non-differentiable point to emerge. So this is the key condition which helps us to apply the Caustic skeleton and derive it for the three-dimensional universe. So what you can do is you can take the whole of the Lagrangian space to be your initial manifold, and you can apply this condition. And what you will end up with is that 1 plus mu has to be 0, which is the fault condition, which is exactly when the density spikes. However, if you apply this same condition now to the fault manifolds, you get the next condition, which is known as the cusp manifolds. The A3 manifold, which consists of the fault manifold, but in addition you see that the directional derivative of the eigenvalue field in the direction of the eigenvector field has to vanish. And this gives you the first higher order caustic, which is known as the cusp. If you continue this, you get a whole list of caustics where you can see that we go from the fault caustic, which is a shell crossing region, to the cusp, to the swallowtail, to the butterfly. In addition, we find that there is an umbilic and a parabolic umbilic caustic, which we will study in more detail. So this classifies the formation history of the different elements of the cosmic web, because these different elements can be directly linked to different geometric shapes in the late-time universe, as we see that the cusp corresponds to a wall and the swallowtail and the umbilicus corresponds to filaments in the universe. So you see that there are multiple channels through which the filaments and clusters can form in our universe. If we now take this knowledge and take a Gaussian random field and initial conditions and calculate its eigenvalues, then you already see that you get a spider web-like nature in the initial conditions. And in fact, these are the proto-filaments and the proto-walls in our universe. We can see this in more detail in this simulation. So on the right you see an embodied simulation. On the left you see the Zeldovich approximation, which is a linear approximation of structure formation. Even though the Zeldovich approximation does a terrible job at late times, we can still measure its caustics, and we will show that the caustics of the Zeldovich approximation give us a first impression of the structure in our universe at the late times. So here on the left you see in green the first eigenvalue field, which plays such a seminal role in the structure of the cosmic web. You see in addition that we plotted the fault and the cusp condition, which is denoted by the red and the blue curve. If you now take this network and you map it onto the current universe using the embodied simulation, you see that exactly where you would expect a multistream region to form, you see that the caustic skeleton has placed a line, so to say. So you see the red region, which is the fault, with shell crossing region, and in addition you see that the cusp really tracks the geometry of the cosmic web, and in particular the filaments in 2D and the walls in the three-dimensional universe. In 3D you see that you start from a homogeneous universe, and as time evolves you see the formation of Zeldovich pancakes, which are sheet-like structures which form this interconnected universe we see today in cosmological surveys. So how can we use this to study filaments in 2D? Well, you could say let's just take these cusp conditions, which are here on the screen, and let's sample these. And you can see that the cusp manifold nicely tracks the filamentary nature of the cosmic web. However, there's a problem with going this way. The Eulerian flow to clusters biases the blue line to be in clusters. So the clusters attract the different elements of the Lagrangian skeleton. In addition, the Zeldovich approximation fails in clusters, as you can see that the blue line gets wind up. So in order to really describe the filaments, we feel like we have to go one level deeper. So what we can do is we can say, well, we won't like to be on the blue line, but we would like it to be of maximal stretch. So if we Taylor series the displacement map X, then we find that you have this stretch condition, which is really the gradient of the X map inner producted with the tangent direction along which we stretch. And if we apply this to the Caustic, then we find that this really is described by the second eigenvalue field and not the first eigenvalue field. So if we work through the maximal stretch condition, then we find that we want a Caustic, which is denoted by the left conditions, which in the addition is maximally stretching, which is denoted by the directional derivative of the second eigenvalue field in the second eigenvector direction. So this is a very nonlinear constraint which allows us to denote the points which are stretching along the filament. And these are denoted here by the blue points in the blue filament regions. So what we can now do is we can take these conditions on the eigenvalue fields and the eigenvector fields, we can turn them into nonlinear conditions on the derivatives of our primordial gravitational potential. And since we know that gravitational potential is a Gaussian random field, we can calculate the distribution of the eigenvalue fields subject to these conditions. And this will be a non-Gaussian distribution which we can calculate. Now, starting from this distribution, we can sample it using a Hamiltonian Monte Carlo scheme. So here on the right you see the red point, when every red point represents a sample of the derivatives of the gravitational potential subject to these Caustic conditions. Once we have these derivatives, we can use the Hofmann-Riebeck algorithm to extend the Gaussian random field to the complete box. And this is our non-linear constrained Gaussian random field theory sampling method, which we use in this work. So after extending, we get a Gaussian random field which can serve as initial conditions for example, an embodied simulation. If we run these embodied simulations, we see that we get a nice filamentary structure here in the center of the box, where we control the formation of the filament, the formation time, the length scale at which it forms, and finally its orientation. You see that this does a beautiful job at predicting the filamentary structure of the cosmic web and the points, the centers of the filaments. If we take now 1,000 simulations of these conditions and sample that in Eulerian space, calculate the density fields and stack them, then we find that we get beautiful mean fields of the density, where you see that as the filament formed earlier, it has had more time to form more denser structures, whereas if it forms at a larger length scale, it will also be a more tough, long filament. So this is exactly what you would expect. So how do we use this to actually study the three-dimensional cosmic web? What we first can do is we can see how it looks like, how the geometry looks like. So here you see a typical Zeldovich pancake, where the red region is really the cusp region, and the blue region is the shell crossing region. And what we would like to do is we would like to capture how this red disk is described in terms of the initial conditions. So what you do is you say, I would like to be on a cusp manifold, which is this condition on the first eigenvalue field being 1 over the growing mode, and in addition that the directional derivative of the first eigenvalue field in the first eigenvector direction vanishes. But in addition, we find that you would like the directional derivative of the sum of the second and the third eigenvalue field in the direction of the second and the third eigenvector field to vanish. And once these vanish, you know that you are on a point on this cusp manifold which is maximally stretching, which is kind of its center. If we apply the same logic to the swallowtail caustic, then we find that we get again a maximal stretch condition along the direction of the filament. And also for the umbilic caustic, we find that the initial umbilic condition is that the first and the second eigenvalue fields are equal to 1 over the growing mode. But in addition, we require that the directional derivative of the third eigenvalue field in the third eigenvector direction has to vanish. And these are nonlinear conditions which allows us to sample the universe. So if we take now the umbilic conditions, for example, and sample them using Hamiltonian Monte Carlo method and run an embodied simulation on them, you get a beautiful filamentary structure. So on the left and the central panel you are slicing the density field along the filamentary direction, and you get beautiful banana-like shapes. If you slice it along the orthogonal direction, which here denoted by the red point in the right figure, you see that it's really a dense filament and that there are walls sticking out of the filament. If you do this now for the cusp wall, then you see that you get a beautiful cusp wall-like structure in our universe. So this is a constraint simulation based on a single point subject to the cusp condition. If we do it for a filament, we get a beautiful filament here denoted by the green line and the blue line. And you see that you also have the formation of two cluster regions in white. If we take the full universe, then we can see how this forms an interconnected network which captures the geometry of the cosmic web. And this is what we would like to study in more detail. So what I have shown is that you can use the caustic conditions which are based on the formation history rather than the morphology of the universe to classify the different elements of the cosmic web. I've identified new conditions which demark the proto-walls and the proto-filaments in the initial conditions of our universe. After 40 years of work, after Zeldovich and Arnold's insight into Lagrange catastrophe theory and its application to the large-scale structure, I'm very happy to say that we are now fully ready to consider these techniques and use these techniques to systematically study the different elements of a cosmic web. So there are numerous things which we would like to do with these methods, but to name a few, we are currently investigating how the presence of filamentary structure influences the formation and alignment of galaxies which are embedded in the cosmic web. We are currently using reconstructed initial conditions to map the caustic structure of our local universe, so we should be able to tell exactly which elements of our local universe are formed through which formation channel. Finally, we are using machine learning methods to build a pipeline which should allow us to identify these caustic structures directly from redshift surveys. So in principle, we can use these initial conditions to train a model which recognizes the geometry of the cosmic web and can constrain physical parameters directly using this mathematical language on redshift surveys. So thank you very much for listening. I highly recommend seeing Benjamin's talk for more details.